Okay, if you're watching this on YouTube, do not forget you have a quiz tomorrow on projectile motion. Okay? And don't say, oh, I wasn't here yesterday. No. Okay? Everybody's taking the quiz tomorrow on projectile motion. Right? So don't, oh, I was at math relays. I'm sorry. You're still going to take the quiz. All right, so let's talk about what's going to happen with this lab. So, what you're going to do is we're going to look at the variables that play into centripetal force. And we're going to look at centripetal force equals mv squared over r. So this lab is going to boil down to manipulating these four variables: centripetal force, mass of the stopper, velocity, and radius. So we're going to change all of these variables in a controlled manner. So the first thing that you need to do is you're going to take a glass tube like such. And a lot of these tubes, like you're going to have like a smoother edge and kind of a rougher edge. Like this one, the bottom side of this is like the tape's kind of sticking over it, but I've got a smooth edge up here on top. So you're going to take a piece of string and you're going to feed that through the tube like so. Like so. In. So to one end of the string, you are going to secure a rubber stopper. On the first, I've got a whole bunch of different sizes of stoppers. You want to start off with kind of a medium-sized stopper. You don't want one really, really, really small. You don't want one really, really big. So you're going to tie that on there. Do not worry about the radius for now. So you got this. Boom. Give that a couple of ties. And you're set. At the other end of the string, just tie a simple loop. Make the squirrel, take it like this, make the squirrel run back to the tree. So then you got something like this. And then make the squirrel run around the tree, dive back through the hole, boom, you got a nice loop on the end of it. So here's what we're going to do. We're going to take, like for example, I'm going to take this 200 gram mass and I'm going to attach that to the bottom. So then, as I swing this rubber stopper around, what I can do is I can make that basically look like it's levitating. So if I change the condition, if I make it go like a little bit faster, I can change that condition. If I kind of slow it down some, I can get like a different radius. But here's the whole point of this lab, and here's the key assumption that we're going to make, is that the weight of what's ever hanging down here is what's creating the centripetal force to keep that rubber stopper in motion. So on trials 1 through 4, okay, trials 1 through 4, you're going to start off and you're going to take a 100 gram mass, and you're going to hang that from the bottom of the string. On the first ones, I tell you what radius that you want to use. The radius is sketchy, mainly because of the fact that if I'm swinging this thing around and I tell Danny to measure the radius, that's going to be tough to do right now because Danny's got to like hold up a meter stick and try and measure the radius of a spinning object. That's tough to do. So here's what you're going to do. You're going to lay out, so here's the tube. And here's going to be the rubber stopper like this. And then here's this string. So you're going to take a meter stick and you're going to measure from the top of the tube, okay, not the bottom of the tube, the top of the tube. And you're going to measure out 0.8 meters. So you're going to measure from here to the center mass of the stopper. You're going to lay that on a meter stick and you're going to measure that to be 0.8 meters. So then when you do that though, then you're going to take a marker and I'm going to put a mark on the bottom side of the string. So the top is the 0.8 meters. So that's from here to here. That's the 0.8 meters. But the mark, when I get to that point, is going to be on the bottom side. Here's the reason why. Because now, when I begin to spin this thing around, I know when I put that mark right there at the bottom of that tube, like this, now I know I have a radius of 0.8 meters up here. So the top is the actual radius, okay? Here to here, that's 0.8. The visual mark is on the bottom side, so that way when that gets to this point, I know I have a 0.8 meter radius from here coming out, right? Got that. So, what we're going to do is I'm going to be a member of the Danny and Preston lab group. So I'm going to get this thing going. So Danny and Preston are going to, once I tell them that I'm set, that I've got that rubber stopper going at that radius, they are going to time 10 revolutions. Now, the hardest part of this lab, oddly enough, is counting to 10 and timing it, okay? So let me give you some words of advice about lab protocol. Do not count out loud, okay? Even though it's just one group, realistically there's going to be more than one group. So don't sit there and go, 1, 2, 3, 4, okay? People are going to want to beat you, okay? You don't have to show off that you can count out loud. Everybody gets it. You can count to 10. This is not a skill set that's unique to you. But here's what you need to do, though. When you're counting these, so if I'm Danny, okay, or Preston, I'm going to be timing this. So what you want to do is pick like a mark on the ceiling, and you're going to go, when this mark crosses a particular point, start your stopwatch. But here's what you have to count, though. So if I'm going around like this, okay, I'm going to start it when it crosses the edge of the F equals MA sign. So I'm going to start it and go, start 1, 2. But I'm not going to count, so I'm going to start it when it gets there. But when it gets back, that's going to be 1 revolution. 2, 3, 4, up to 10. So I'm going to start it, but then when it gets back, that's the first revolution. So when you compare times, Preston and Danny are going to compare their times. And if you got like 1.37 seconds and 1.57 seconds, that is too big a gap, okay? Somebody didn't count to 10, okay? Literally. The hardest part of this lab is counting to 10. Some people will go hardcore. Though, actually, I've seen kids do this. They will lay on the floor and look up, and they will count that rubber stopper as it goes around like this. I'm not saying you have to do that, but I'm just saying if you want to be a hardcore, hey, I want to get good data, that's one of the things that you can do. So, here's the mathematical side of this. So, in this situation, what I just did, I had that 0.2 kilogram mass hanging from the end of this. So I'm going to multiply that by G, and I'm going to get 1.96 newtons. So on this data table, okay, so if I'm doing the 0.2 kilogram mass, I'm going to have a scale back there. We're going to measure the mass of the rubber stopper. That is a home run deal. There's no variation on that. You just find the mass of it. The total time, that's going to be the time for 10 revolutions. So Dan is going to count 10, Preston's going to count 10, okay? We're going to compare the two. If they're off by quite a bit, we're going to redo that trial, okay? Don't bail on this, oh, we'll just take the average. No, somebody can't count to 10, okay? Those times should be pretty close together. I've given you what the radius is going to be. So on this first column, where it says centripetal force, What we're going to do is we're going to let that be the weight of whatever is hanging down. So in this situation, like on trial 2, where it says centripetal force, I'm going to put down 1.96 newtons. So the hanging mass times G is going to get you the centripetal force, okay? If it's 0.1, hey, that's going to be 0.98. 0.2, 1.96. So period is going to be for 1 revolution. So Danny, if you know how long it takes for 10 revolutions, how are you going to get the period for 1 revolution?
Divided by 10.
Yes, just divide it by 10. That's why we're going to use 10. Okay? So the period of 1 revolution, just take the total time and divide that by 10. Move the decimal place. That's all you have to do. You're going to have the circumference. Now, on trials 1 through 4, the circumference is going to stay the same. Preston, why is the circumference going to stay the same on trials 1 through 4?
Because we have the same radius.
Yeah, we're keeping the same radius, okay? Since the radius stays the same, the circumference is going to stay the same. And then you're going to calculate velocity by taking the circumference and dividing it by the period of 1 revolution. Now, here's the math side of this. Centripetal force equals mv squared over r. So we're going to do a deep dive into the mathematics of this. So on trials 1 through 4, keep in mind that m is the mass of the stopper, because that's what's going around in the circle. That mass is not the mass of what's hanging from the end of the string. That's the mass of the stopper, okay? So on trials 1 through 4, am I going to change the mass of the stopper? No, that's the same stopper all the time. I'm not going to change the radius. So I could actually get this as a constant. If I wanted to, I could take the mass of the stopper and divide it by the radius, and I could get that numeric value as a constant. So what that means is that that's basically saying, oh, centripetal force equals kV squared. Oh, it looks like a quadratic, and it is. So what you're going to do, over here on page 2, you're going to end up drawing a total of 3 different graphs. So on trials 1 through 4, we're going to put velocity on the x-axis, and we're going to put centripetal force on the y-axis. Now, here's the story. As the velocity gets bigger, okay, as v gets bigger, what has to happen to your centripetal force? Preston.
Increase?
Yeah, because both sides have to remain equal. Now, are they going to increase on a 1-to-1 ratio?
No.
No, why?
Because of v squared?
Because of v squared. So here's what I want you to think through. And I don't care how you think through it. There's a couple of options. On trials 1 through 4, you're going to make the centripetal force bigger and bigger and bigger. Okay, you're going to go from 0.1 to 0.2 to 0.3 to 0.4. Okay, this side is going to get bigger. This ratio of mass of the stopper to radius is a fixed value. You don't have to calculate it, but just understand that it's just a constant. So the only way that I can create more centripetal force is if the velocity gets bigger. Now, you look at this and go, okay, hey, great. Velocity equals 2 pi r over t. I'm not going to change the top part of this because I'm not going to change the circumference. So that's a fixed value. So to get a bigger velocity, what has to happen to the value of t?
That's the decrease.
It has to become smaller. So that's the trend that you should see. So in trials 1 through 4, when we do this, you should see the value of t becoming smaller and smaller and smaller, because that rubber stopper is going to be going faster and faster and faster to create more and more centripetal force. Okay? Now, on 5 through 8, you're going to pick one of these values. 0.2, 0.3, I don't care, pick one. I don't recommend that you pick 0.1, because 0.1 is tough to do because it isn't much centripetal force. So on trials 5 through 8, you're gonna change the radius. So on 5 through 8, here's how this is gonna look differently. You're gonna still go back to mv squared over r. So on this one, I'm gonna keep my centripetal force a constant. I'd recommend that you use 0.2 kilograms or 0.3, okay? This side's gonna stay constant. I'm gonna keep the same mass of the stopper on trials 5 through 8. So the mass is gonna stay the same. But what I'm gonna do is I'm gonna alter the radius, okay? And when I say change the radius, I mean change the radius. Like you want at least 10 or 15 centimeters in between the changes in the radius. Now, this is where it gets a little bit dodgy. So when you're doing that part of the lab and you're changing that radius, you're gonna have like different marks on this string. So use them like in different color or something like that, so that way you're not always trying to find like the same blue mark. So pick a radius, then you're gonna change it. I'd recommend that you go somewhere between like 0.5 meters, maybe up to a meter, something like that, okay? Now, here's the bigger picture. The centripetal force is gonna stay the same. The mass is gonna stay the same, okay? That's the mass of the stopper. So, as the radius gets bigger, you're gonna make the radius bigger and bigger and bigger. What's gonna happen to the velocity? Is the velocity also gonna get bigger, or is the velocity gonna get smaller? Danny?
It's going to get smaller. Oh, it's going to get larger.
Because I want the same number over here, right?
Okay.
So if I'm dividing by a bigger number, my velocity also has to be getting bigger.
Okay.
But, Preston, there's only 2 of you, so everybody, we're just gonna alternate question. So, is the velocity and radius gonna change in a 1-to-1 ratio?
No,
Why?
because velocity squared.
Because velocity is squared. So here's what's gonna happen in trials 5 through 8. You're gonna keep the same centripetal force, you're gonna keep the same mass. So as radius gets bigger, velocity has to get bigger, because you're gonna keep the same centripetal force. So the last set of trials, you're gonna keep the same centripetal force. You're gonna keep the same radius. But now you're gonna alter the mass of the stopper, okay? Now, Danny,
Yes.
I'm gonna keep the same centripetal force. I'm gonna keep the same radius. As mass gets bigger, what has to happen to the velocity?
It gets smaller.
It gets smaller. Preston, is it gonna change in a 1-to-1 ratio?
No,
Why?
because velocity squared.
Do you see the pattern? Okay? So, your velocity is gonna be like your great equalizer in terms of how this is gonna play out. Okay, so it's Wednesday, so what you should be able to get through is trials 1 through 4, okay? And then if you can get through 5 through 8, that's great. So tomorrow, here's what's going to happen. Tomorrow is Thursday. Yes, for those of you that are watching this on YouTube, tomorrow is Thursday. So what that means is that tomorrow you're going to walk in, you're going to get that projectile quiz out of the way. It's not going to be a long quiz, at most 1 page front to back, okay? That's going to get done, then you're going to spend the rest of the time finishing collecting the data, okay? So for those of you that weren't here today, you guys are going to have to hustle to get a whole bunch of data collected. If you're nice, maybe we'll share, but we'll see. Okay, all right, let's go do science. So Danny, stop you on the camera.
Okay.
And you guys have the convenience of having the teacher in your lab room.